Hello. So this video will address t-distributions, and let me make the initial comment that t-distributions only are concerned with numerical traits. You will never use a t-distribution with a yes-no trait or a categorical trait. So, a tad bit of history. William Gossett worked for the Guinness Brewery, and in the very, very late 1800s and the early part of the 1900s, he did a lot of testing on beer, and he couldn't really test a lot of product. A couple of reasons. One, it would cost a lot, but probably he'd get drunk. So what he saw was that the normal distribution didn't really apply for small sample sizes. So he developed what's called the student's t-distribution, and he called it a student because he wanted to get this material published, but Guinness didn't want their competitors to know about this. So they allowed Gossett to publish this under a pseudonym, and he chose student. So what is happening? Why do we have to have t-distributions? Well, what happens is, if you recall from sampling distributions, what we know is if you have a yes-no trait, we know that the sample proportions, the p-hats, will cluster right around p, right? And they'll do so in a normal distribution, and they'll spread out by standard deviation formula, square root of p, 1 minus p over n. Whereas if you have a numerical trait, right, the sample y bars will cluster around mu, right? Also in a normal distribution, and they'll spread out by the formula sigma over square root of n, where sigma is the standard deviation of the population. All right. Well, what you can see is that p is the center of the distribution, right? And standard deviation is the measure of spread of the sample proportions around this center, which is the mean p. Well, you can see that the mean here is in its own measure of spread. So these two move together. Once you know p, you also know how standard deviation moves. So they're linked. But here, do you see mu in its own measure of spread as far as the sample means go? No. So that means the center here and the spread are not linked. So these are linked. These are not linked. So these move together, these move independently. And because of that, you have a lot more error, especially when you're talking about small samples. So what Gossett found was that you have what are called t-distributions. So if you look at the normal distribution, let's suppose this is the normal distribution, then a t-distribution might be, it's going to be something that, well, if it's a very small sample, it'll have a slimmer center and fatter tails. So compared to the normal distribution, you have this here, fatter tails and a slimmer center. Now, mu is still the same. The center still stays the same. Again, it's how the sample means behave. So what happens then is, as the sample size increases, the t-distribution become normal. Okay. Now, what do I mean by that? What I mean by, as the sample size increases, what will happen is these tails will come down a little, and a little bit more will go into the center, right? So what will happen then is you have more of the sample means coming into the center, and the tails go down. But what, of course, this does mean, though, that there's a lot more variability. So again, if we look at the normal curve, right, and we say here's an axis, and we look at, for example, a t-distribution, right? For a particular value, let's say a value out here, then what you see is the chances of getting if it were a normal distribution, then the chances of getting that value or something more extreme would be very small. However, with a t-distribution, look at how much more likely it is, the chances that that sample mean will be quite a bit further from the mean, right? So there's a lot more variability. There's a lot more variability with these t-distributions. And also there's a family of distributions. T-distributions are so sensitive. They're very sensitive to sample size. That actually there's a family of distributions. So what you'll have is something like this, where depending on the sample size, the tails will go up, right, if their sample sizes are very small. And as the sample size increases, the tails start to come down and the y-bars tend to cluster more around the center. But there's literally a t-distribution for each sample size. So what happens then is you have a formula called degrees of freedom, which is abbreviated DF, and DF is sample size minus 1. So you'll have to actually identify which t-distribution am I working on, because there are so many. And essentially the way you'll find out is degrees of freedom is 1 less than the sample size. Now, let me just mention that when they say large, sample sizes get large enough that the t-distribution becomes normal. Technically, the t-distribution becomes normal when you actually reach the population size. That's technically. However, really, the central limit theorem shows us that as long as the sample size is about 30, that it's approximately normal. The t-distribution become approximately normal. So they're good enough to, they're good enough to go ahead and do good calculations with them. Now, one little last comment on degrees of freedom. This isn't the level we want to go into what is a real degree of freedom as far as statistics is concerned. But just to give you an idea of what do we really mean. Well, let's just say you had somebody who, let's say you had the sum of 4 numbers equals 100. And I asked someone to give me a number under 100, so there's the constraint, you have to give me numbers under 100. But let's say somebody says, oh, here, I'll give you the first number is 12. And then I ask another person, oh, give me another number under 100 that I can work with, and somebody says 27. And then I asked another person, and somebody says, oh, 48. Well, so far, these 3 people, though there were some constraints, they had a lot of freedom as to the number they could give me. But this last one has absolutely no freedom, has to be 13 for the rest of the numbers to be equal to 100. So you can think of that a little bit as what degrees of freedom are. Now, how does all this t-distribution, how is it going to affect us? Well, as I mentioned, it's only to do with numerical traits. And essentially, if you recall, for confidence intervals, previously with a yes-no trait, what we did is we calculated a confidence interval by saying sample proportion plus or minus z times standard error of the sample proportion. So here we used z. Now we're going to use, for a numerical trait, we're going to use y bar plus or minus t times the standard error of y bar. So now we're going to use the t and look that up in a t multiplier table. And let me see if I have one nearby. Yes, I do. Now this t multiplier, we'll look at how to use this, but instead of one line, we now have a lot of values. Now, it's not hard to use this table. There'll be another video showing you how to use it. But essentially, because of all the extra variability, there's a lot more math that's needed to be able to estimate correctly. And the other way that you'll see it for hypothesis tests, right, you'll see that you'll need, instead of a z-score, where you had, basically you're looking at for how far is my sample proportion from the mean over the standard deviation. Okay. Now you'll be using a t-score. and you'll say how far is my sample mean from what I'm assuming is the mean in my hypothesis test over the standard error of y bar. So you'll see it here, and then over here in the hypothesis test where you were using normal CDF from one z-score to another, right, z1 to z2, to get your p-value, now you're going to use t-CDF. Right, so normal CDF versus t-CDF, and here you're going to use first t-score, second t-score. This is exactly the same thinking. I'm going from one particular z-score to another. What's the area in between? The same thing. The only thing we're calling it t's instead of z's. But here you'll have the degrees of freedom, and that'll be very important to put in there. So those are the changes you're going to see, right? It's just big picture changes. And the last thing I want to address is it can get kind of confusing. How do I know when I actually use a t-distribution? So technically, if the population standard deviation is known, that is sigma, if it's not known, you absolutely have to use t-distributions and t-scores. But if it is known, then if your sample size is less than 30, you also still have to use t-distributions. But if it's greater than 30, then you can already go ahead and use a normal distribution or z-score. All right? So thanks for listening.